All right. Welcome back to the penultimate meetup. Got one more after tonight. So I think our plan for tonight is Angela and I were talking ahead and make a game time decision. So we're going to get through predictive modeling, which was technically part of last week's slide deck. And then depending on the time and how we feel, we'll do Bayesian. If not, we can do the little introduction to Bayesian next week because it won't be on the final exam. I think, as we mentioned, it's sort of like I consider it kind of bonus material, and just to kind of set you up for success in future courses. As is this topic, because I don't know how much this is, not a lot in the textbook, but let me start because I can't remember. I should have flipped through these real quick. So the way I kind of think about the predictive modeling here. So up to this point, right, we talked about inference and, statistical modeling for like inference point of views, and a lot of, the assumptions and the checks we're doing are, largely from an inference point of view. So, and then I'm going to move into more of a predictive point of view. Now, what you're going to find, right, we talk about predictive models, and then in data science, we talk about AI, and machine learning. Machine learning and AI in its current form, to me, is really just forms of predictive modeling, right? We're making statistical models where we're trying to predict outcomes. The models that you're going to use to do those are often the same models that we've been using for a century to do inference, to understand the relationship between variables. What's a little bit different when you get into the machine learning predictive modeling viewpoint is sometimes we're a little less interested in sort of the details about our independent variables in relation to our dependent variables. What we're just interested in is if at the end I can make a new prediction given a new data set, and how well can I accurately make that prediction. Okay, so depending on your point of view, how you're going to approach assumption checks, multicollinearity, all of these kinds of things may, variable selection, things that, even last night people talked about which variables to keep in their model and trying different ones. That's all great. It's just we're going to sometimes let some violations go as long as we can demonstrate that we can make an accurate prediction. And so what I want to talk about is just kind of like that different way of evaluating the quality of a model, right? It's kind of a different way of thinking about it. So we're picking up from logistic regression, and this comes up right around when you learn logistic regression, because and it's kind of useful even in a logistic regression point of view, because we don't really have something like, we don't have an R-squared measure that gives us a good model fit with generalized linear models. You can Google around, and there are sort of pseudo R-squared measures for GLMs, or generalized linear models. But they're somewhat problematic. There are other fit statistics like a key information criteria, or AIC, and those are fine, but AIC in particular is very data dependent. Remember we were talking about this little toy data set where we had the number of hours studied, and whether or not they're going to pass an exam. Right. And so remember, what we're really fitting is sort of the log odds, right? So we have probability of success, quote unquote, over failure, and we're taking the log of that. All right. And so if we want to make a new prediction, we want to know the probability of, passing if you don't study at all. Right. And so it's not quite as simple as just substituting in a value into a regression equation like we would in algebra and solving for y. Right, because our left hand of the equation is a little bit different. So if we go back a couple, I got to look at the regression, output. We have an intercept and a slope, right, which are part of, in that link. So here's our intercept and our slope. Of course, we're going to substitute 0 in here, and what we need to do is exponent or take to the power e both sides, so we can get this ratio on its side. And you can solve this down. And so we end up with a probability of about 1.6%, right? And if we look at the plot, right, that's corresponding to something down here, right? So obviously very small. So we can get, right, so we don't get exactly, in the case of linear regression, right, we get a value that kind of makes sense. So here we're getting a probability. So our predicted values are always going to range between 0 and 1 in the case of classification problems from with something like logistic regression. And here's another one for 4 hours that we kind of go through. And of course we can see that through here, right? Because what we're doing is we're using that logistic function, right? And if you see here, this is where that linear combination is, where we have our slope or intercept, right? And so we can kind of fit that in, and so if we had a half hour where we have like a 3.4, 3.5%. Oh yeah, thanks for that note, Angela. Okay, so we're going to start to tackle this and by using what's called a confusion matrix. And so some of this, like this upper part of this quadrant, shouldn't be too unfamiliar, because what we're going to end up doing is something akin to what we did in null hypothesis tests, where we're going to have situations where we can commit type 1 or type 2 error rates, right? But in the case of prediction, we often classify them as either true positive, false negative, or true negative, right? So true positive, true negative, that's ideally what we want, right? And how are we going to get that? So what we want to do is look at we're going to make predictions and see how often we are correct. And then there's a whole bunch of other things. This is kind of the full slide. As you go through the program, you'll fill in some of these other bits around. So let's look at a little bit more of an interesting example, but a classic in the predictive modeling or machine learning world, which is predicting who survived the Titanic. People have been for years trying to fill out this data set, and it's rather complete now, and it's kind of built into R. So we have this variable, right? Survived, which is a yes, no variable. And then we have a whole bunch of other things like what class ticket they had. We actually have names here, which is kind of odd, but we have sex, age, siblings, and the like. And so we want to use those to try to predict. Now, when you attack these kinds of problems from a prediction point of view, we're going to want to split our data set into two. What we're going to do is train a model with a certain percentage and then validate with the other set. We don't want to use the same data set to both train and validate, because that inevitably is going to overfit the data. So we kind of want to hold some data back to do it. There's no hard and fast rule on this. 70-30 is something I see pretty common. Sometimes I see 75-25. If you have a really, really large data sets, you can go higher than that. So you want to train with as much as you can. And there are other kind of intermediate steps. So I'm only kind of tackling this from a broad point of view. There's other things like n-fold validation that you can do within, but we won't go into that tonight. We're just going to take the sort of most broad approach, where we're just going to randomly select 30% of our data and kind of put it to the side. So we could see here, right? And the other thing we see off the bat is that over 61% of the passengers did not survive the Titanic, right? And that to me is going to be our baseline for which we're going to do comparisons, right? So, and I'll say a little bit more about that, but the simplest model I can conceive of is I could predict that no one survived the Titanic. And if that was my strategy, or that was my model, right, I would be correct 61.5% of the time. So that's going to be, so we want to improve upon that. So here's our logistic regression. Where's my split? All right, so you can see here, here's where I did the split. So I just randomly selected 70%. Those are my training rows. I did this the old base R way, right? And so if I put the minus, this gives me the rows that aren't in that one. So now I have two data frames, train and test. So you can see here, I'm running the logistic regression on the training, and I'm using class, sex, siblings, and I can't remember what Parch was. I think it was what level they were on. So you can see Parch is not a significant predictor. Siblings is, sex is, as if you've seen the movie, you probably know that. And then class is also a predictor. So, but I can leave this in here, right? This is a pretty large p-value, so I may want to leave that and take it into account. But for now, we can leave it because I'm not really terribly interested in what each individual variable is, right? I'm going to move on and just look at the predictions. And so here I can use the predict function, which is going to give me the log odds from the distribution. So you could see here, and I did a density plot, and I have two densities for survive and not survive. So you can see on the prediction on the x-axis, the red line here are those who did not survive, right? And just to kind of satisfy our intuition here, right? It's skewed on the left-hand side, right? We the hump is on the left-hand side, right? So our model is indicating more of those values fall on the left side. And then for those that did survive is higher on the right-hand side, but there is still a lot here. So it looks like our model just on the surface does a pretty good job of identifying who's not going to survive. And then for those who are going to survive is kind of a mixed bag. It's a little bit better on the right-hand side, but not on the left. But let's be a little bit more concrete about this. So here I'm going to, for now, just kind of split at 0.5. That's not always the best place to split, and I'll show in a moment. But right, so since the predicted values range between 0 and 1, and we have a little imbalance here, but not too bad. If the predicted probability or the predicted log odds is greater than 0.5, I'm going to call that a survivor, and if it's less, I'm going to call them a not survivor. So if I do that, now I get this confusion matrix. And so here I'm just doing a contingency table where I have on the rows correspond to what I predict, and the columns correspond to truth. And this is on the training set. I'm still working with the training set for now. So if I if I predicted, death and they did not survive, 52.7% of the passengers in the training set, and those who I predicted survival and actually survived was 25.9%. So if I add these two cells, right, that's the accuracy of my model, which works out to be about 78.71. So that's definitely an improvement, but there's some problems here because I used the training set. So this is my error, right? And so this would be my type 1 error, and this would be my type 2 error. But because that overfits, right, let's actually do the proper thing, right? So here I'm looking at the validation set, the test set, right? So it's 62.5% did not survive here. So it's roughly the same, but there's a little bit of sampling variation there. Now I'm going to call predict here using my logistic regression, but what's key here is this new data parameter, okay? And because I want to do the predictions on this new data set. And so similarly in the last slide, if it's greater than 0.5, I'm going to consider them survival, otherwise not. And here I can look at my confusion matrix, right? So in 55% of the chances, I predicted no survival and they did not survive. In almost 25% predicted survival and they actually survived. So the sum of those, which is 80.15%, right, is the sort of accuracy of this model, right? That's how accurately I predicted survival from the Titanic, right? And recall over 17.5% better than the baseline, okay? And that's really important. That's what you want to compare. Don't get hung up. 80% seems like a lot. In this case, it's actually quite good, right? But it's not 80% above 50, right? It's always going to be based upon your base proportion. So that's to me is the primary way in classification problems where you're predicting, true or false outcomes or dichotomized outcomes, how you want to evaluate the quality of your model, right? And so I'm often going to do this, and you can do this by changing variables or trying a whole host of strategies, right? If you do our 622, 624 sequence, which are electives, You learn about unsupervised and supervised learning, and a lot of that stuff has to do with ways that the unsupervised stuff of things you can do to reduce the dimensionality, try to improve the quality of predictive models. Okay, there's another way of looking at this, which is called the receiver operator characteristic, or ROC curve, right? And so what this is going to try to do is plot the true positive rate against the false positive rate. So we're just going to pull out those two bits of information. And I have a utility function I wrote because I have my own version of a ROC curve I like to look at. The area AUC is the area under the curve, which is often reported in machine learning journals. So 0.5 would be essentially guessing. So anything above that. So a 1 would be a perfect prediction. So it is a way of kind of looking at that. I also have in here this threshold with minimum cost or maximum accuracy. So on the left side, this is what's the ROC curve. So the way this curve is drawn, right? So remember I said in my initial pass, I said I'm going to cut at 0.5 at the predicted probability. So what this is going to do, what the curve does, it says, well, what if I cut it just above 0 all the way to 1, right? So if I cut at 0, what's the false positive rate versus the true positive rate? So it plots that as it's growing from 0 to 1 on where that threshold is to classify it, right? And so that's what we're getting here. So as you get this black line lifting up, so like I said, if it was 50-50, that black line would fall right on this blue line. That's essentially guessing. So what we're looking for is a lift away from this blue line. So like I said, a perfect model would go straight up and straight over, and that would be 100% area. If you end up with 50%, well, you just landed on the blue line, and so you just have that. Okay, so the and then over here on the right-hand side, right, is a cost curve. Actually, I'm going to go to this one first because this is, I think, a little bit easier to understand. So this here on the right-hand side, as we're going from left to right on that threshold, we're calculating the accuracy. Okay. And so the place where the accuracy is the highest is actually at 0.495. So I use this a lot to determine where I want to do that threshold. I don't just pick 50-50 because there's some issues with doing that. So in this case, I would split at 0.49 to do my confusion matrices. What the cost does, right, is it associates a cost with, in this case, you can see the cut is the same. So you can weight the type 1 and type 2 error rates. If you, so there's a parameter to this function that allows you to do that. So you can decide, well, I want to penalize a type 1 error rate more than a type 2 error rate. You can do that and say, hey, I want to penalize it by 2. So, and that will affect the cost curve. So there's different ways you can do that as you go through. But I think the accuracy, because I tend to keep my type 1, type 2 error rates, weight them equally. I just wanted the overall accuracy to be as high as possible. So it turns out this 0.45 is right here, corresponds to this point right here, right? And really what you're looking for is the place on this curve that is furthest from the blue line perpendicular to it, right? So that's kind of where that falls. Now, I just want to say a little bit more about accuracy. So as I mentioned, you want to compare to what your base rate of success or failure. Success, not necessarily, I don't mean that to have particular value, but it's true false, right? And I think Silicon Valley is particularly problematic here, right? And I use this one particular study. This is a link, you can read it. Lo, Su, and Xing, which are data scientists at Facebook in 2016. And this got a lot of news press because they said, well, we could accurately predict our Facebook users' sexual orientation with 90% accuracy, and they used a combination of support vector machines, logistic regression, random forest methods, right? So logistic regression, even using the things we learned, right? And people were freaking out, in some ways, maybe rightfully so. It's I think Facebook does some questionable things with statistical models, but from my point of view, I was like, oh, 90%, like that seems like a lot. That seems really great, except when I saw this, it was closer to 2018. So I went to Gallup, who does these national polls. And in 2018, at least according to Gallup, 4.5% of the American population identified as LGBT. I should probably make this Q plus, but it was LGBTQ or LGBT in 2018. Right, which means 95.5% identified as heterosexual. So I see this and I go, well, here, I have a better model than Facebook's. I'm just going to predict everybody's heterosexual. And I'm going to be correct 95.5% of the time, better than Facebook's 90%. So this is kind of a cautionary tale here. So one of them is when you're trying to predict rare events, it's going to be extremely difficult to do with statistical models, unless there's some really strong indicator within your data set. So my advice is, avoid it if you can. Sometimes you can't. Angela and I, in our work with DAX and in our last study, we're trying to predict things like retention at institutions that have 70 to 80% retention rates. And so that really squeezes how much our data can kind of reveal. And so getting any lift when you're starting at 70% is really kind of great. If you have a data set where you're trying to predict something that's roughly around 50-50, right, then it's much easier to get larger increases in sort of your accuracy of predictive models. So just things to be aware of what you want to try, and sort of predicting rare events is kind of really problematic. So this actually, I initially encountered this as part of my dissertation work. So a lot of what I do is something called propensity score analysis, which is a quasi-experimental design. And in the first step of doing a propensity score analysis is you want to predict whether or not someone uses this treatment. So we're trying to adjust for selection bias. So what we're predicting is whether or not somebody chooses to go into a treatment. And we're going to try to predict it on as many observed variables as we have as that individual. So I tend to work mostly in education. So I'm looking at things like social economic status, parents' education, gender, sex, high school scores, anything like that I might have. And I want to try to predict why someone might be take that treatment. Okay. Now in my dissertation work, I was looking at, the difference between charter schools and traditional public schools. Well, nationally, about 3% of students in the United States attend a charter school. So I am trying to predict a very rare event, right? And there's lots of strategies that you can use, including upsampling and downsampling that you'll go into in other courses. But what happened here is because I was using logistic regression to predict that, and then I'm using the fitted values or the predicted values from the logistic regression as something that we call a propensity score, which is defined as a conditional probability being in the treatment. So we actually interpret it in that context as a probability. What was happening is my dissertation chair was like, well, these propensity scores look weird because they weren't any larger than 0.2. And so I did some exploration and did some simulation to look at this. So this is, I wrote a function, get simulated data. This is in a package called multi-level PSA, but what I really want to do is just let's get to the figure. And so what I've done here is, so I have, you could consider this not survived, survived, false, true, control, treatment, whatever context, right? It's a 0-1 outcome. And if we start down here, right? So I fixed this particular example is I'm going to have 100 treated individuals. Okay. This bottom figure here is, I ran, I think 20 or so simulations. Yeah. 20 simulations per one. Now at this bottom level, right, I have exactly the same number of ones as zeros or treatment as controls. And then what I've done here is the little red here is the density distribution for the control. And the teal here on the below is the density distribution of the treatment. So it's akin to this plot here, but I kind of just drew them top and bottom. Okay. Then over here on the right-hand side, so so I did this. So this represents 20 different random samples. And so these 20 points here correspond to the maximum value of the fitted values from that model. And these points here represent the smallest value. And so that this little bar here is the median of all the lowest values. And this is the median of the maximum value. So I'm trying to capture the range, right, of the fitted values from the logistic regression. And here's the distribution where I have exactly the same number. And so the next one here is now I have twice as many control as treatment, right? Twice as many zeros as one, right? That's all I changed, right, in this. This is all coming from the same base data set. This is just a simulation. And so look at here, like the minimum value in the fitted values goes down and the maximum came down all the way up. So you can kind of see, so I have 2 to 1, 3 to 1, all the way up to 10 to 1, where I have 10 times as many controls or 0 units as treatment units. So all else being equal, the range of fitted values from the logistic regression are going to shrink, right? So this is just sort of a cautionary tale on interpreting the fitted values from the logistic regression directly, because that, and this is going to be particularly problematic when you have imbalanced data. And what I mean by imbalanced is one class in this dichotomous variable is much larger than the other. So 3% to 97% is highly imbalanced, but so is 70-30, right? So, and this is going to be, this could be a problem. This is really just a problem in the interpretation of the fitted values. Oftentimes the logistic regressions still work fine. So if you go back and use like this strategy and you have a ROC and you use this accuracy curve, will give you a cut value, but in the, in this example, the cut value might be something like 0.2 or 0.1, and that's fine. But this is just kind of an artifact of how logistic regression kind of works. Okay, so I have a bunch of additional resources here. So this, I think I showed this last week. So this is the path to log likelihood. So this is a little article that goes into some of the assumptions of why we don't just do an ordinary least squares all the way down to this particular figure that shows, right? So this is the curve we're fitting, and these are the log values. So that might be useful. This is the write-up for that Shiny app that I showed last week. This is the package. This is a great little video. I think this is StatQuest. Is that right? Yeah. If you haven't seen, I think this is, he does some really great jobs, some really great visualizations explaining things. So there's 2 parts for maximum likelihood, and actually 3 parts. So some additional resources that you can look at if you want to hear a different explanation. So let me pause here and see if there are questions about predictive modeling or logistic regression or anything, quite frankly.
I have a quick question. So for predictive modeling, to stir away from biases, will we have to be careful of how we collect our data?
Oh, for sure, right? This is a massive concern, I think, in the field right now. And I think I brought this up. Didn't we talk about this when we talked about the binomial distribution? I used Milgram as an example, sort of my very, this goes into the question of ethics in data science, right? So if there's bias in your data, there will be bias in your model, okay? But that's not to say I am also a big fan of George Box had a famous quote that says, all models are wrong, some are useful. So yes, absolutely. And I'm a big proponent. I think we need more social scientists going into data science to kind of bring in that perspective. But yeah, that's a good question. If the data is biased, and there are a ton of examples. That one of the more egregious ones was Google's image classification algorithm when it first came out. It classified African Americans as gorillas, which is pretty offensive, but it had to do with the fact that they just didn't have minorities represented in their classification data, or in their training data set. So yeah, you should look for it. There's lots of great books and articles. The one I like, she's Math Babe on Twitter, Kathy O'Neill. Weapons of Math Destruction, I think, is a fantastic book. There, you can get it on Audible if you prefer an audiobook. I read it driving, on a trip once. I think that's a great place to start. There are other great books on it. I think she just has a new one just came out too, but her writing is great. It's very entertaining. Some of the stories are kind of just funny, and then some are a little bit more serious. So good question. I don't have a great answer other than explore.
So like with the example of like the prediction model, like to see if like somebody's like their sexual orientation based on like their profile, when they're creating these like these models, like how are they like accounting for like maybe like when they were collecting like their data on this, like it was like based on like, I don't know, like is there some type of like buffer with these like like these predictioning models, or is it that they like take on that like limitation?
Yeah, unfortunately, until recently, until some of these more egregious problems or ethical lapses, I think a lot, and this is sort of the Silicon Valley, I think, ethos and philosophy is like move fast and break quickly, or I can't remember the exact phrase, but a lot of times they just build these models without thinking about whether or not they should build these models. And so yeah, you kind of take that in, and like in the sexual orientation one, they ended up getting a lot of flack afterwards as people started to look at their study. But I think they were somewhat shocked about it because they didn't even think about it. That it's just this is the data that's in front of me. I work at Facebook. I have a whole bunch of likes about people, and a lot of them kind of provided their orientation in some way. So let's build a stats model, right? So I don't think, like, you can't fix that through a statistical method, if that's what you're asking. It's more of a philosophical, it's an ethical, it's a sort of broader question.
Might I suggest that more diversity in the data science field might help with that?
I would completely agree, Diana. I was going to share a story, but I don't know if I want a recording because I'm not sure if I'm supposed to know. But I think about that a lot. Like yeah, I think about it a lot.
Save it for after the recording.
Yeah.
Thank you for answering.
Yeah, no, I'm glad you're thinking about it, and I could tell you, since I've joined as a full-time faculty in the program, part of one of my goals is to increase the diversity of our program. But it's really, it's really difficult, but we're trying. Diversity, like, was it Amazon, I think, that was using predictive models in the HR process to screen applicants, and then they were like, how come we don't have any women? Well, you don't have any women working there in your training set, right? Oh, here's another one that just came up. I actually got into a little bit of a debate with somebody from College Board. We're talking about predicting student success. They're trying to defend the SAT and the ACT. And one of the things they brought up as a defense is, like, in their data, they have studies that show that for a lot of minority or underrepresented populations, the SAT is actually over predicting their success. And I was like, well, that's great. However, you would never see under predicting because you're using that same test to decide whether or not they can come. So the there's a bias in how you're using your measure and in the prediction of college success. And I think she was a little taken aback by that point of view, because they, as a psychometrician, they try to design it to be, unbiased. And I think what we're realizing in that field, right, a lot of this is also measurement issues, right? That they try to take all context out of the test, and by taking all the context, they actually can increase biases that way, right? For those in New York City, if you're a student in New York City and you have a question about trees in a forest and you've never seen a forest, you kind of get hung up on that and kind of miss the point of the question. So anyways, there are biases all over the place. I think we just need to be aware of them. Angela, do you have anything to add? I think as the white guy on here, I should stop talking for a while.
I just recommended a documentary on Netflix. It's called The Social Dilemma. Jason, I think we talked about that one. Yep. It opened my eyes to how data science and social media is, just be careful, because they collect our data without, we work hard with these IRBs, right? As social researchers, we have to get approval for everything, any of the data we collect, but out there, we have data, they make money collecting our data, and then they use it for, some use it to their advantage. And that's sickening, I think.
Yeah, for sure. All right. I'm going to say, I realize it's only fewer than 16 slides. So I'm going to just do the Bayesian so that we can have a shorter class next week and we can talk about questions or other next steps for you. And if we don't finish, we don't finish. This is, so on the Bayesian analysis side, I think my primary goal is just to kind of contrast this to the frequentist point of view. And so I start with the resources. So I think my favorite book to learn, or the most approachable book, is John Kresge's, often called the puppies book, but Doing Bayesian Analysis is sort of a great introduction. Andrew Gelman's book is fantastic, but gets super technical very quickly. It's a very dense read. If you're looking for summer reading, Weapons of Math Destruction, can't highly recommend that enough. But The Theory That Would Not Die is just particularly if you're interested in history, it's more of a history book than a stats book. Although she does a great job of explaining, I think, Bayes' theorem in a very approachable way, non-technical way. But it's a theory, Bayes, I think, first published on this in like the late 1800s. And it's only really come into popularity in the last 2 decades, in part because it's computationally intensive. But it has been used by applied statisticians or researchers for years, particularly in industry. The most famous example that she goes in this book in like how it's used in different places, but probably the most famous use of Bayes is the Enigma machine by Alan Turing. So the way, so he used a Bayesian methods to crack the Germans' encryption codes. And so that's a great way. What I'm going to do is heavily borrowed / stole from Rasmus Bath. I did a workshop with him almost a decade ago, but he has a 3-part video on YouTube that I think is really great. He's great. He does a lot of in the R Bayesian community. And actually, I just added this. This is a kind of a cool article that's getting a more brief introduction, because what I'm going to talk about 2 examples, because I think it's easier to talk through an example. The second one is actually looking at a game that Bayes wrote about in his actual first paper on Bayesian analysis. So if you go back to the probability chapter, this formula, I think, appears in chapter 3 or something, but it didn't pay a whole lot of attention to it. But from a probability point of view, right? So this is what Bayes' theorem is. We want to predict the probability of A given B, where we have all the other pieces, right? We know the probability of B given A, probability of A, right? All of these pieces. And here's a classic example where, in the medical field, right? So we say we're going to stipulate, or we know from sampling our census data that 1% of women have breast cancer, right? And so the complement of that is 99% don't. We know that 80% of mammograms detect breast cancer when it's there, therefore 20% miss. And 9.6% of mammograms detect breast cancer when it's not there, right? So that's the false positive. So we could write this out as a 2x2 contingency table. We have true positives, true negatives, and false positives, false negatives, right? And so in these kinds of situations, right, the sum of the row or sum of the columns equals 100%, right? And so the question is, how accurate is the test, right? And so there's, it's not, the test is not 80% accurate, right? It's a little bit more complicated. Because if we get a positive results, all it means is we're somewhere in the top row, right? And remember, the columns equal 100%, not the rows. So we can't simply add that up. So the way we get there, right, is it's the, when we think about probability more generically, it's the probability of the desired event over all probabilities, right? And so we can kind of simplify this formula down a little bit, and I'll show in just a second, right? So we know the probability of positive test given cancer. We know the probability of cancer. We know the probability of positive test. So we want to know the probability of cancer given a positive test. So it ends up to be about 7.8%, right? So that's sort of from the probability point of view where it is, right? So we can simplify that formula in this situation where it's really the chance of a true positive divided by the chance of any positive result. If that's what we're interested in, we can do that. And so like Chris's like little picture here. So where is this useful? And kind of walking through an example in sort of a modeling point of view. So the first example I like is, in population estimates or trying to find anything when you have a small amount of information. Okay, so if we want to know how many fish are in a pond, right, we could count them all, right? But that seems not practical or probably not even possible, right? So we want to use some kind of other sampling procedure. And this is what I'm going to propose as our strategy. We want to catch some fish. We're going to mark them, return them to the pond, let them swim around so that they have a chance to go anywhere in the pond, catch some more fish again, and count how many were marked, right? So we can actually do this. We can get in a boat. We're going to go out. We're going to catch 20 fish. We're going to mark them, return them to the pond, come back a little bit later, catch 20 fish, and I see 5 of the 20 I caught were marked, meaning 5 fish were caught a second time. All right. So from this information, we want to estimate how many fish are in the pond. Okay. So how are we going to do that? Well, with Bayesian, and often one of the more controversial things about Bayesian analysis is we're going to come with some kind of prior information. Now, I'm going to start with what I would call, or what we call, a naive prior. And we'll talk about a non-naive prior in a moment, right? So a naive is, well, I don't know. There has to be at least 20 fish because I caught it. And looking at the fish, I have to put a cap on there. I'm going to say there can't be any more than 250 fish. It's a very small pond. So I'm going to guess there's somewhere between 20 and 250 fish, all of equal likelihood of occurring, right? And so here I'm actually going to do it 100,000 times. So right now you're going to start to see why this method is become more attractive as personal computers and fast computers become available. Because I'm going to do something 100,000 times. All right. So what am I going to do here? I'm going to have n fish, right? So I'm sampling from 20 to 250, 100,000 times with replacement, right? I look at the first 10, right? And this is what the histogram looks like, right? So now I have this vector of n fish of a length 100,000, and they all have values somewhere between 20 and 250. This vector represents my guess of how many fish are in the pond. All right. So I'm going to try all of these. So then the next thing I need to do is some way of generating data. So I have to define a generative function. Okay. So here's my pick fish, right? So this is my generative model. So what is this doing? So I'm going to pass in a parameter, which is a guess of how many fish there are. So looking at this, my first guess is going to be 183. So I'm going to pass 183. So what am I going to do? I'm going to repeat 0 and 1, right? So I'm going to take 183 and subtract 20. I'm subtracting 20 because that's how many I picked. I have to have at least that many, right? And then, so I'm going to repeat. Oh no, that's right. That's how many I catch. So I caught. So 20 fish, 20 fish get a 1, and number of fish minus 20 get a 0, right? So I have a vector here, length and fish, with 20 of them as 1s and the rest 0s, okay? Then from this vector, I'm sampling 20, right? And then I'm just summing it, right? So that's, in essence, I'm repeating that experiment, right? So I'm going to say, well, if there's 123 fish, if I caught 20, mark them, put them back, how many do I get back? So I could do that. And so what I'm going to do is save that and marked, right? And I'm going to go through on the number of draws, which I thought was 100,000. Is that right? Yeah, 100,000. Okay. And so I'm saving that. So in the first example where I had 183, I ran this function and I got 2. Okay. Then I ran it with 162. I also got 2. Then I tried it with 35 as my guess, and I got 12. Okay. So I did this 100,000 times, right? So this is essentially this vector now represents the number of marked fish I caught the second time, given the number of fish in the pond that I started with. Okay. So what I'm going to do here is my posterior distribution at the end. So I'm looking at n fish, and I'm keeping only the ones where n marked is equal to 5. Why 5? Because that's what I saw in reality. That's the only thing I know for sure, is I went out in my boat, caught 20 fish, marked them, and caught 5 of them that were caught the first time, right? That's the only thing I know. So I'm keeping that. And here I can plot it, right? So here's the distribution of the number of fish in the pond that resulted in getting 5 marked, right? So my guess is the pond has roughly 100 fish in it. And I have here, I did a 50% kind of like a pseudo confidence interval, right? So I'm 50% sure it's somewhere between like 75 and 125 or 130 or so is how many fish are in the pond, right? So from that one bit of information, I was able to generate this data. So, and as a Bayesian, I approach this and say, the only thing that's true is what I saw. And so I generated data to see how often I would see what I saw. And so so my confidence interval is not derived from the central limit theorem about something I can't see. I actually generated the data. So my confidence is driven from this posterior distribution. Okay. So this is where things get interesting and sometimes controversial, but we'll see. My experience is not terrible, right? So I'm some expert. I'm an expert fisherman, and I come in and say, I believe there are 200 fish in this pond. Okay. So instead of starting with the uniform distribution, I can use that prior information to define my prior distribution, right? So here I'm going to use a random binomial distribution centered on 200, right, as such. So this is going to feed into my guessing. Everything else is the same, right? All of this is the same. I'm running that through, but instead I'm just using these data as my inputs. And so here's my posterior distribution. So even though I guess 200, right, I still, my median is a little higher than 100, but my 50% confidence band here still captures 100. So, so I would say that was a pretty bad prior, and I picked it bad on purpose to show that even with a bad prior, the model kind of came out okay. So why would you want to use that, right? So in studies, right, if one of the Bayesians say to frequentists, you always start with the null, but you ignore all of this literature or prior research, right? Why start with the null, right? Why not define the prior distribution based upon prior research, right? And to me, there's something compelling about that. It's something interesting, but I also see why you might want to do a null distribution. But the point being, right, what I want to say is, like, the frequentists are making their inferences based upon this notion of this sampling distribution, that there exists some distribution if I were to take an infinite number of samples. The Bayesian is making their inference based upon the distribution that I generate based upon the truth that I see. So the Bayesian says that the data is the truth, not the sampling distribution. Okay, so that's kind of a major contrast and can kind of result in a lot of different things. So Bayes first introduced this by, and this is what statisticians at the time did, is they made up these games and tried to talk about the probability. So his game was, I'm going to throw an 8-ball on a pool table. We're going to assume the pool table has length 1. Okay, we're just going to call it length 1, and there's going to be there's going to be an observer, right? So the table is perfectly level, other kinds of stipulations. We're going to record the location of the 8-ball, but not tell you. All we're going to tell you is we're going to throw subsequent balls and tell you if the ball landed to the left or the right of the 8-ball. And that's the only information you're going to get. So I wrote a little Shiny app, and this little article here kind of goes into it. If I can find the app. Okay, here we go. All right, so here we are. So I have a confidence range. I'm just going to do 50%. We can look at histograms or densities. I have the histogram here because there's an artifact. So here's my prior on the right-hand side. So there's this dip off, and so the histogram just show that it is indeed a uniform distribution. So I'm going to start with a naive, right? I have a uniform distribution, so the ball can be anywhere from the left edge to the full right edge. The first throw, I learned that the ball landed to the right side of the 8-ball. I'm gonna make sure I say that right. Okay. So the ball landed to the right side of the 8-ball. So think about that, right? So intuitively, if the ball landed on the right, the 8-ball should be more to the left side of the table, right? And so what I do here, right, my generative model is I'm going to try every, I think there's like 100,000 observations here. Each one is a guess somewhere on the table. I'm going to take that guess. I'm going to randomly draw a number between 0 and 1. And if it's to the right, I keep it. And if it's to the left, I throw it away. And so I end up with this posterior distribution, right? So this here is summarizing it after one iteration. This would be my guess of where the 8-ball is, and I'm 50% sure it's within here, okay? So let's get another ball. Then second throw also lands to the right, right? But what I'm going to do here in iteration 2 is I'm going to use the posterior from iteration 1 as my prior in iteration 2, right? Because it's the same 8-ball, and I already learned something in the first toss. So you can see this distribution kind of goes a little bit more to the left. We can see, okay, I'm kind of honing in on it. I could do another one. Third toss to the right. So the posterior from iteration 2 becomes the prior in iteration 3. And now I'm really sure the 8-ball is getting over here, and I can do, but now I got a left, right? So let's look what happens. So my posterior from iteration 3 becomes my prior in iteration 4. I run it through my generative model, seeing how many times I now get left, right? So it shifted over a little bit. And so I got another left. And so what are we at? 5. Let's do one more. Okay, now we got another right. So you can try this later. Every time is a little bit different. Usually I get it after this number. So we're, I'm doing 5,000. Okay. Oh, here it is. I click this box and there it is. There's the 8-ball. So I had captured it in the first 2 and went a little bit to the right, but right, this is 6 pieces of data, right? And I was able to kind of pretty closely kind of hone in to where it is. So these kinds of problems, Bayesian methods are really, really powerful to kind of get to. And so if you read that book, The Theory That Would Not Die. So in addition to, right, for the Enigma machine, what Turing was able to do, right, is he knew enough about how the Germans were doing stuff that he could throw out some data sets or some seeds that he didn't need to try, because he learned from previous days that these wouldn't be it, right? It's been used to find submarines, or there was a case, I think, post World War II, where there was a nuclear missile at the bottom of the ocean, and they were trying to get it before the Russians got it, right? And so they used Bayesian methods to create a search grid and updating each time they looked at it, right? So these ones where you have, a small amount of data, but as you can see, right, each of these iterations are doing 5,000 random samples. So it becomes pretty computationally intensive rather quickly. That's a very quick crash course introduction to Bayesian. Like I said, it's not on the final exam. You're not going to be tested on it, but I think it's becoming so popular, and I just wanted to kind of give you some insight into how this works. If you're comfortable with bootstrapping, for me, I became a big fan of bootstrapping for a while. And so this kind of becomes a kind of a natural extension. You can think about writing things up that way. This becomes a pretty natural extension to that. I threw the 1-minute paper in the chat, and I'm happy to take questions.
I have a quick question. Sorry, just wanted to check. We have this project tomorrow, 12. Should we use the same link?
Yeah. Use this meetup link. Good question. Yep.
Okay. And also quickly, would you like us to show something on the screen, like our R Markdown or some slides, or what would you like us to show on the screen?
Yeah, whatever you feel comfortable with. Most students create a slide deck, but whatever you're most comfortable with. Some students do pretty well talking through a document if you want to have like an R Markdown, but if you're not comfortable that way, I think slides are a little bit easier.
Okay.
Would be my recommendation. Yeah.
Yeah. Okay. Thank you.
For the 1-minute paper, I know you use it for like data gathering. Do you want us to use the topic of logistic regression or Bayesian analysis on the dropdown?
Use Bayesian so I can separate this week from last week.
Okay.
Good question. Yeah, we ran out of time, and we'll revisit how we split up. This probably needs to be separate topics, but. All right. Have a great evening, everyone.